In this lesson, we're going to talk about wireless networks. So wireless networks, what do they allow you to do? They're going to allow your users to roam within a coverage area and still remain connected to your network. This is essential when we talk about devices like tablets and laptops and cell phones when you don't want to have to use cellular data. So your wireless networks or your wireless LANs, also known as WLANs, their popularity has really increased exponentially. I mean, it's very rare you can go into a business nowadays that doesn't offer a public Wi-Fi hotspot. Think about Starbucks and Panera or even the Green Turtle. They all have wireless networking for you to sit there while you're eating your dinner and use your cell phone or use your tablet devices there. They're convenient to use and they expand network access throughout a room, a floor, a building, or even a campus if you're dealing with a school. AACC, our main campus, no matter where you are on campus, you can pick up Wi-Fi. Same thing with this building here at the Cyber Center. There's lots of different wireless networks out there. By far the most common, though, is 802.11, which is wireless networking that you think of when you talk about Wi-Fi. There are some other options out there that are used for personal area networks, things like Bluetooth, infrared, and near-field communications. But really, when we talk about wireless networks, most people are thinking Wi-Fi, and they're thinking 802.11. So there's two different modes that we can operate our wireless network in. We can operate it in ad hoc mode or infrastructure mode. When it's ad hoc, the devices are going to connect to each other without a centralized access point. If you think about like the Nintendo DS, if you have kids, they can actually play directly between the two DSs without any kind of central access point. They're not going to get to the internet, but they can play with each other, right? With infrastructure wireless networks, we actually are going to go to a central point. This is that same star topology we talked about before. And you can see a picture of that in the bottom right corner. We have these 5 computers that are accessing the central access point using that star topology. These devices can communicate either wireless or wired through that wireless router or access point. This is traditional Wi-Fi that we use in our home and office networks. If you look at your thing, you go home tonight and look at your access point. This is how you're operating in an infrastructure method. So wireless router. Your wireless router is going to be your gateway device and base station for your wireless devices to communicate with and connect to the internet. So this often you'll have one device that combines many features into one. So for instance, here's a picture of a Verizon gateway. It provides not just the fiber optic modem, but it also provides a router, a switch, a firewall, and the wireless access point in addition to it, which we usually refer to as a WAP or an AP. As you notice here in the diagram in the top, we have an internet service provider. They have their modem. The modem then connects to the wireless router, which provides access to the wireless devices. Then a switch is connected to connect the PC. In the case of this Verizon device, it's combining all of those devices, all of those networking devices into one box for you. And that's what you have in most places. If you use a Comcast modem or a Verizon modem, you'll see that at home where you have it all combined into one box. But really it is 4 or 5 separate functions there. An access point itself is not going to do routing for you if you have just a wireless access point. Its whole function is just to act as a media converter. It's going to expand the wired LAN into the wireless domain. You can't use it like a router to interconnect networks. It's just going to act like a hub. And a diagram of that shown here, where we actually have these 2 access points connected to a switch. That switch is then connected to the router, which is connected inside the modem off to the internet. Those access points are just acting like a hub. They're just giving you that media conversion capability. This is going to connect your LAN to the wireless devices through the access point, and they'll be on the same subnet. And all of your clients on the access point act as a single collision domain like a hub. So if you remember when we talked about hubs, this is a security issue for us. Because if somebody's on your wireless network, they can see or listen to all the traffic if they put themselves into promiscuous mode. So there's 2 different ways we can configure our wireless access point when we're in infrastructure mode. One is called the Independent Basic Server Set, the IBSS. And this is where you have no infrastructure, it's just the ad hoc LAN. So here we have the 2 laptops talking to each other. They have no way of getting onto the wired network and getting out to the internet provider. So these guys are only talking to themselves. Not extremely useful, right? If we go to the Basic Server Set, the BSS, we have both laptops connecting to a wireless access point. That access point ties into the switch, which goes to the router and off to the internet. This is a network with only one access point. This is what you have in your home environment for most of you. This is also you have in a small office or a home office network. Extended server set, on the other hand, is what we use here at the college. Because this building is too big for a single wireless access point to provide all the coverage we would need, we have multiple access points like we're seeing here. So some of the laptops connect to one access point, some of them connect to another. They then tie back into the switch, and they work together to provide continuous coverage throughout the building. So even though you don't know it, whether you're sitting on this side of the building or the other side of the building, to you it looks like you're on the same wireless network. But really we have multiple access points that bring you into that network. In addition to that, we can actually mesh together multiple technologies. If we do a mesh topology of these wireless technologies, we actually have multiple wireless devices that may or may not use a centralized control system. The range of these combined wireless is going to define the mesh cloud that we're using. And we can use multiple technologies. In addition to wireless, we can use things like cellular or microwave. So a real simple example of this is if you have a, like one of those hotspots. You guys ever seen those little hockey puck type hotspots? You can buy from the cellular provider. It gets an internet connection via cellular and then provides a wireless access over Wi-Fi to the 5 closest devices to you. That technically is a wireless mesh network because it's coming in as cellular and then redistributing it out to you in a local area network as wireless. So with wireless networks, we have to have antennas because we have to be able to get that signal to and from the access point. Our coverage area is going to be based on the type of antennas we're using though. Most of us in our home and our small businesses have what's called a fixed antenna, meaning they're not going to move. They're just going to be put in one position and stay there. In enterprise networks, you can have multiple different types of antennas based on your needs. Your antenna is going to be effective based on how far you want to cover, the type of coverage you're having based on the pattern, environment, whether using it inside or outside. For instance, if I'm outside, I'll get more distance than I would inside, because inside I have to deal with all the walls that we have that are blocking our connections, right? And if there's interference with other access points, that can cause an issue as well. So we can use different antennas to shape our patterns. And I'll show you some pictures of that too. So the first one we're going to talk about is the omnidirectional antenna. And this is a wireless access point with an omnidirectional antenna. Omni meaning all, so it's all directional. It's going to radiate power evenly across all directions. And so if we just put it in the center of the building, we should have a fairly good coverage. At your house, the wireless access point you are given by your cable provider or your internet provider is a omnidirectional antenna. So if you put it in one corner of the house, the other side of the house may not get as good a coverage. You want to try to get it in the center of your house. Another type of antenna we have instead of omnidirectional is unidirectional, which means one direction. And as you can see here, this is used for something like connecting 2 buildings together. We would put the antenna on top of the building, pointed at the other building, and the direction will only go between those 2. They won't go out the other side. This is going to focus all of its power in a specific direction. And the benefit of this is it's going to avoid interference with other areas, and it can get you a further distance because it's putting all of its power out in one direction. A good example of that you might see sometimes they'll bring this up on a test. It's called the Yagi antenna. And an example that's here in the upper right corner. It's a directional antenna. Wherever direction you point it at, that's the direction the signal is going to go. This is common at exterior networks, not inside buildings. Inside buildings, we're normally going to use an omnidirectional, or one that we can put cutouts in certain zones. So the way we transmit our data can be done different ways depending on what version of wireless we're using. When we do spread spectrum, we have 3 different models of that. The first one is DSSS, which is direct sequence spread spectrum, and it's going to modulate the signal over an entire range of frequencies using signals called chips. It's more susceptible to environmental interference because of the fact that it's using the whole spectrum, and it uses the whole spectrum to transmit, which means that it's fairly easy to know where it is. To see a picture of that, just look at the top here, the 16 megahertz spectrum, and how it's all being used by one big data transmission. Frequency hopping, on the other hand, it's going to hop between predetermined frequencies in the spectrum. And this is going to give us better security because it's going to continually hop around. So if somebody's trying to listen into our conversation, they have to know where we're going to be and at what time. OFDM, orthogonal frequency division multiplexing. It uses a slow modulation rate with simultaneous streams over 52 data streams. You can see a picture of that there on the bottom, where we have the OFDM. Notice we have 4 different streams here, and we're sending the data over it. In actuality, we would be using 52 streams. This allows us to use much higher data rates while resisting interference between the data streams and is used in newer networks. Only DSS and OFDM are commonly utilized today. Frequency hopping was used in some of our early generation networks for security, but again, it gives up way too much of the frequency is not being used at any given time, so it decreases your bandwidth, so we don't use it nowadays. For the A+ exam, you don't really need to understand this slide. If you go into Network Plus, you'll have to understand this a lot more. In A+, just the idea that it exists is sufficient for us as technicians. If you're running into problems with wireless, this can be helpful with troubleshooting. But again, it's not something you're going to be able to configure or change. Based on the wireless you have, if you have wireless N or wireless B or wireless A, it's going to determine which of these standards you're using. You're not going to determine that yourself. So wireless standards. This chart, the first 3 columns, are things you need to memorize for the exam. Okay? Specifically, wireless A, B, G, and N. Okay, those 4 in the middle. Knowing the frequency it operates at, 5 gigahertz, 2.4 gigahertz, or in the case of N, both 2.4 and 5 gigahertz, and the speeds. 54 for A, 11 for B, 54 for G, and about 300 for N. The reason you have to know this is you're going to see questions on the test that ask that. And they'll ask it in many ways. They may ask you which of these networks supports 54 megabits per second, and the answer would be wireless A and wireless G and wireless N, because all of them would support at least 54, right? They may ask you, you're using a baby monitor that has 2.4 gigahertz frequency. Which of these networks would not interfere with it? And the answer would be A, because it uses 5 gigahertz, or N, because it can use 5 gigahertz, right? Or if you had wireless G operating at 2.4 and you have a baby monitor operating at 2.4, you can cause interference. So we'll talk about that as well. Wireless N and wireless AC are the 2 newest ones that we use nowadays. They use what's called multiple input, multiple output, which means they have multiple antennas for transmission and reception. Generally, you'll find they'll have 3 antennas or more. So, as far as frequency goes, I just said you had to memorize the frequencies for these, right? Whether it's 2.4 or 5 gigahertz, depending on which one it is. For A and N, we can operate at 5. For B, G, and N, we operate at 2.4. The frequency is going to be determined based on the type of wireless you're using. Each of the bands has specific frequencies or channels that you can set your wireless access point to. The best practice is to set them at 1, 6, and 11, because that way it gives us separation. And the reason for that is because when you use a frequency like here on channel 1, it's not just going to be on 1 as a straight line. It kind of has this hump to the frequency. So it actually bleeds over into channel 2 and 3. Same thing with 6, it actually bleeds to the left up to channel 4 and down to channel 8. And so we want to make sure these humps aren't being overlapped because that can cause interference. So by selecting channels 1, 6, and 11, it will avoid interference and give you a better signal. And that's specifically used in the 2.4 gigahertz band for wireless B and G. There's 1, there's 6, and there's 11. Like I said, it's not a straight line, it's that big curve of a hump. So we don't want those to overlap, that causes interference. So again, we can cause interference lots of different ways. Some of the devices that'll cause interference are other wireless access points. If you live in like a condo or an apartment and you've got 30 people in the same building, there's a lot of different access points within range of you. And so you got to make sure you all are not on the same channels using the same names and overlapping each other, because that's going to slow down your networks. If you have a cordless phone or a baby monitor, they operate in the same frequency of 2.4 gigahertz that wireless B and wireless G operate at. Microwave ovens are also operating at 2.4. So if you have your wireless access point sitting in your break room at work, and every time somebody goes to microwave some popcorn, the network drops, that's the reason, because it's causing interference. A lot of wireless security systems also operate at 2.4 gigahertz. You can have physical obstacles, like the walls. If they're made out of concrete or thick materials, the signal's not going to propagate through. If you have a refrigerator, it's made out of a lot of metal, it's going to block it. Thick wood cabinets, that'll block it, right? So you want to keep that access point out in the open area so the signal will go stronger. And then you can also configure your signal strength. You may want to have it stronger or weaker depending on your use case. Generally, most people want it stronger so it reaches further. From a security standpoint though, having it too strong can be a bad thing, because if your signal is going outside your building to the parking lot, then an attacker can sit in the parking lot and get on your network from there. So you want to think about those things as you're building your network. So when we talked about wired Ethernet, we talked about the fact that it used carrier sense multiple access collision detection. So it knew when a collision happened. With wireless networks, we actually do a thing called collision avoidance. So it still does the carrier sensing where it listens first, but then it tries to avoid collisions. So what happens is it listens for the transmission on the channel. It sees if it's safe to transmit. If it doesn't hear anything, it sends out a signal called a request to send. That request to send waits for an acknowledgement from the other people, and if it doesn't receive an acknowledgement, it'll start a random back-off timer. This way it avoids a collision instead of detecting having to retransmit. It can just wait a first time. So it's a little bit more efficient than the Ethernet use that we have. The second kind of wireless networks we talk about are Bluetooth. And with Bluetooth, we use these for personal area networks. It's things like our mice and our keyboards, our smartphones and tablets, printers, projectors, and other devices so that we can connect from one device to another. These are relatively short range and low speed. We have class 1, 2, and 3 devices. Class 1 goes 100 meters. It's the furthest. Class 2 is 10 meters. That's most common. That's what you're going to find in most devices. And class 3 is 1 meter. Again, these are low speed. We're talking 1 to 3 megabits per second. So you're not going to use this for data, but for mice and keyboards and stuff like that, it works just fine. Infrared. Infrared is a short-range, low-speed, line-of-sight connection. We don't use infrared a whole lot anymore. We used to use it a lot with the old Palm Pilots, and you could see that down in the image in the bottom right corner, where we had a Palm Pilot, would have to physically be in sight looking at the infrared receiver, and they would send data. The problem with these is they were very, very slow. They were good for connecting keyboards and mice, because again, they were low bandwidth. But now that Bluetooth is popular, most things have switched over to Bluetooth. Some laptops will still have infrared for things like remotes, but again, Bluetooth is pretty much taking over. If you need infrared, they do make infrared to USB adapters, but most of the time you're not going to run into infrared anymore. So wireless interfaces. Our wireless cards can be built into our machines. Most laptops have them built in. If you need to put one in and there's not one in your laptop, you could put it in through a mini PCIe expansion slot, or you can always use USB. When we deal with our lab, we'll actually go ahead and hook up a wireless adapter through USB to our laptop, to our desktops using USB. If you're having a desktop, you can also buy full-size expansion cards for PCIe X1 slots or PCI expansion slots. Here's a sample question for you. Which of the following 802.11, which is Wi-Fi standards, can operate at both 2.4 and 5 gigahertz? A, B, G, N, or AC? N. Yeah, N was the one that was dual band. So A operates at 5. N and AC both operate at 5. And then B and G and N all operate at 2.4. So yeah, know those frequencies because those are the types of questions you're going to see.